The universe is hiding its rulebook from us. We see its effects, the galaxies spinning, the stars shining, the very expansion of space itself, but the fundamental forces behind it all remain just out of sight. Today, we are going on a journey to uncover 30 of the most profound theories about these hidden powers, from the dark energy tearing the cosmos apart to the quantum fields humming in the emptiness between atoms. By the end, you will see reality not as a fixed stage, but as a dynamic puzzle with pieces we are only beginning to fit together. What if gravity is not a fundamental force, but an illusion emerging from something deeper? Could our entire three-dimensional world be nothing more than a holographic projection? We are about to explore ideas that challenge everything we think we know about physics and existence. What do you believe is the most mysterious force in the cosmos? The first theory on our list begins with a mistake, a cosmic correction that rewrote our future. Albert Einstein, when formulating his theory of general relativity, believed the universe was static and unchanging. His equations, however, kept predicting a cosmos that was either expanding or collapsing. To force a static solution, he introduced a fudge factor, a mathematical term he called the cosmological constant. It represented a repulsive energy inherent to space itself, perfectly balancing the inward pull of gravity. When Edwin Hubble later discovered the universe was indeed expanding, Einstein famously discarded his constant, calling it his greatest blunder. But the story was far from over. In the late 1990s, two independent teams of astronomers were observing a specific type of stellar explosion, a supernova, in galaxies incredibly far away. They expected to find that the expansion of the universe was slowing down, gradually braked by the collective gravity of all matter. What they found instead was a shock. The most distant supernova were fainter than predicted, meaning they were farther away than anyone thought possible. The expansion was not slowing, it was speeding up. Something was pushing galaxies apart with ever-increasing force. That something, scientists realized, was Einstein's discarded cosmological constant, resurrected and renamed. We call it dark energy. Think of it this way. Imagine blowing up a balloon with tiny dots on it, representing galaxies. If you stop blowing, the dots will still move apart from the initial breath, but more slowly. That is the old model of a gravity-dominated universe. Now imagine the balloon has a mind of its own and starts inflating faster and faster, all on its own. The dots rush away from each other at an accelerating pace. That is our universe with dark energy. It is not a force emanating from any particle or place. It is a property of empty space itself. Even in a perfect vacuum, according to this theory, space possesses a fundamental, constant energy density. And because there is so much space in the universe, this tiny bit of energy in every cubic centimeter adds up to become the dominant component of our cosmos, accounting for about 68% of everything. The profound, unsettling mystery is why. Why is the value of this cosmological constant so astonishingly small, yet not zero? If it were just a little bit larger, the repulsive force would have been so strong in the early universe that galaxies, stars, and planets could never have formed. We would not be here to observe it. Its precise, seemingly fine-tuned value is one of the greatest puzzles in all of physics, a silent, hidden force writing the final chapter of the universe's story. Dark energy is a ghost in the fabric of space, but what if the other great cosmic mystery is also an illusion? For decades, astronomers have observed galaxies spinning so fast that the stars on their outer edges should be flung into the void. The only thing holding them together, according to our laws of gravity, is the gravitational pull of all the matter we can see, but there is a problem. There is not nearly enough visible matter, stars and gas and dust, to generate that pull. The accepted solution is dark matter, an invisible, mysterious substance that provides the extra gravity. Yet for a small but passionate group of physicists, there is another, more radical answer. Perhaps we do not need to invent a new, invisible particle. Perhaps we just do not fully understand gravity itself. This is the heart of the second theory, modified Newtonian dynamics, or MUND, proposed by physicist Mordechai Milgrom in the early 1980s. MUND suggests that Isaac Newton's famous law of gravity and even Einstein's refinements break down under certain conditions. Specifically, Milgrom proposed that when the gravitational acceleration becomes incredibly weak, as it is in the far outskirts of galaxies, gravity behaves differently. It becomes stronger than Newton's laws predict. Think of it like water. In a fast-moving river, water follows predictable, classical rules of fluid dynamics. But in the almost imperceptible creep of a glacier, ice behaves in a completely different, plastic way. MUND suggests gravity has a similar shift in behavior at extremely low accelerations. This simple tweak to the math produces a startling result. It perfectly predicts the rotation speeds of many galaxies without requiring any dark matter at all. The stars move exactly as fast as they do because, according to MUND, that is simply how gravity works in those quiet, distant realms. Proponents point to its elegant success in explaining the motions within hundreds of galaxies with just one modified rule, a feat that often requires dark matter models to carefully tailor invisible halos for each individual galaxy. The debate between these two camps is one of the fiercest in modern cosmology. It is a philosophical clash as much as a scientific one. Is the universe filled with vast amounts of an unknown substance we cannot see or touch? Or are our most cherished laws of physics, tested so well here in our solar system, subtly incomplete on the grandest scales? For now, most of the scientific community bets on dark matter, citing evidence from colliding galaxy clusters and the cosmic microwave background that MUND struggles to explain. But the theory persists, a compelling reminder that sometimes the most hidden force might be a flaw in our own understanding. The debate over dark matter forces us to question the very laws governing reality. But what if our entire cosmos is just one page in an infinite book? The third theory takes us to the very beginning, to a fraction of a second after the Big Bang, where a concept called cosmic inflation solves several profound puzzles. Why is the universe so large and flat? Why is the cosmic microwave background, the afterglow of creation, so uniform in temperature? The answer, proposed by physicist Alan Guth, is that the newborn universe underwent a period of hyper-fast, exponential expansion. For a fleeting moment, a patch of space smaller than a proton was stretched to a size larger than our observable universe. This smoothed everything out like stretching a wrinkled sheet until it appears flat. But the most staggering implication of inflation is not how it started, but how it might never truly stop. This leads to the idea of eternal inflation. Picture a pot of water just beginning to boil. The bubbles that form and rise are like new universes. In the eternal inflation model, the inflating space, the boiling water, is the multiverse. Regions of this inflating field can randomly drop into a lower energy state, stopping their inflation and forming a stable, bubble universe with its own distinct laws of physics. Our entire cosmos is just one such bubble in an endless, frothing sea of inflating space. Each bubble is causally disconnected from the others, forever beyond our reach. This idea finds a startling home in string theory, which suggests there may be 10 to the power of 500 different possible stable configurations for the extra dimensions it proposes. This vast collection of possibilities is called the landscape. Eternal inflation, then, could be populating this landscape, creating a multiverse where every possible set of physical laws, every conceivable version of reality, exists somewhere. In one bubble universe, gravity might be repulsive. In another, the strength of the nuclear forces could allow for entirely different elements or prevent stars from ever igniting. The philosophical weight of this is immense. It suggests the fundamental constants we measure, like the strength of gravity or the mass of an electron, are not deeply meaningful laws, but mere local bylaws, the accidental outcome of which bubble we happen to form in. The multiverse theory removes the need for a single, finely tuned universe that just happens to allow for life. If every possibility exists, then of course we find ourselves in one of the rare bubbles where conditions are just right. It is a cosmic answer to why we are here, but one that places our reality as a single, unremarkable island in a hidden ocean of infinite possibilities. The idea of a multiverse suggests our laws of physics are local accidents, but what if the emptiness around us is not empty at all? According to quantum mechanics, a perfect vacuum is not a still, silent void. It is a chaotic, seething sea of potential. This is the fourth theory, centered on quantum vacuum fluctuations and the mind-bending concept of zero-point energy. At the subatomic level, Heisenberg's uncertainty principle tells us we can never know both the exact position and energy of a particle. This has a profound consequence for empty space. It means the energy of a vacuum can never be precisely zero. Instead, it fluctuates around a lowest possible value, the 0 point. These fluctuations are not just mathematical quirks. They manifest as pairs of virtual particles and their antiparticles spontaneously blinking into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This is not theoretical speculation. We can observe its effects in a phenomenon called the Casimir effect. Two uncharged metal plates placed incredibly close together in a vacuum will be pushed together. Why? Because the space between the plates restricts which wavelengths of virtual particles can appear. The pressure from the sea of particles outside the plates becomes greater than the pressure between them, creating a measurable force. Empty space, it seems, is alive with transient activity. Now, here is where the theory gets truly cosmic. All this frenetic activity in every cubic centimeter of space adds up to an energy density. This is the 0 point energy of the universe, and when physicists calculate how much energy this quantum foam should contain, based on our best theories, they arrive at a number so catastrophically large it defies comprehension. It should be 120 orders of magnitude stronger than the dark energy we actually observe accelerating the universe's expansion. That is a 1 followed by 120 zeros. It is the worst prediction in the history of science. This staggering discrepancy is known as the cosmological constant problem. It means either our understanding of quantum field theory is profoundly incomplete, or something is cancelling out almost all of this vacuum energy with unimaginable precision, leaving behind only the faint whisper we call dark energy. Some theorists go even further, suggesting that gravity itself may not be a fundamental force, but an emergent phenomenon caused by the collective behavior of this quantum vacuum foam, much like temperature emerges from the motion of molecules. The vacuum, therefore, is not a passive backdrop. It is the most active, energy-dense thing in existence, and we are floating on its surface, only perceiving the tiniest fraction of its true power. The silence of space is an illusion, masking a hidden roar of creation and destruction happening all around us every instant. That quantum foam hints at a deeper layer of reality, one where information itself might be the most fundamental currency. This brings us to the fifth theory, a concept so strange it seems ripped from science fiction, the holographic principle. It proposes a radical idea that all the information contained within any volume of space, including the three-dimensional world we experience, is not contained within that volume at all. Instead, it is encoded on its two-dimensional boundary like the data on a holographic film. Our reality, with all its depth and solidity, could be a vast cosmic projection. The seeds for this idea were planted not in the study of light, but in the darkest objects in the universe, black holes. In the 1970s, physicist Jacob Bekenstein made a startling proposal. He argued that a black hole's entropy, a measure of its hidden information or disorder, is proportional not to its volume but to the surface area of its event horizon. This was bizarre. For any ordinary object, entropy scales with volume. A larger box can hold more disordered stuff, but a black hole, according to this math, stores its information on its surface. Stephen Hawking later showed that black holes can evaporate, radiating away energy and eventually disappearing. This created a paradox. What happens to all the information about the matter that fell in? The laws of quantum mechanics say information can never be destroyed. The holographic principle emerged as a potential solution. It generalizes Bekenstein's area law to the entire universe. It suggests that the maximum amount of information that can fit inside any region is not determined by how much you can cram into its three-dimensional interior, but by the number of tiny, fundamental pixels or Planck areas that can be painted on its two-dimensional surface. Think of it like a modern credit card hologram. The flat, shiny strip holds a seemingly two-dimensional pattern, but when light hits it, a full three-dimensional image emerges. The holographic principle says the universe works the same way. The true, fundamental degrees of freedom, the ones and zeros of reality, live on a distant two-dimensional surface that surrounds us. Our experience of living in a three-dimensional world with volume, distance, and solid objects is an emergent illusion, a projection from that boundary. In string theory, this idea finds a concrete mathematical realization through something called the anti-de Sitter conformal field theory correspondence. It shows a perfect one-to-one dictionary between a theory of gravity operating in a warped volume of space and a quantum field theory living on its lower dimensional boundary with no gravity at all. This is a profound unification. It directly links the fabric of spacetime and gravity to quantum information. If true, it means that every particle, every force, every event that happens here in our three-dimensional world is just a decoded message from a vast, flat cosmic screen we can never see. You are not just in the universe, you are a translation of its surface. The solidity of the floor beneath your feet, the vast depth of the night sky, all of it could be a magnificent, dynamic hologram with a real story written in a hidden, two-dimensional code. If our reality is a holographic projection, then what exactly is doing the projecting? The sixth theory suggests that the very stage upon which the universe plays out, spacetime itself, along with the force of gravity, is not a primary ingredient of reality. It is a secondary effect, an illusion that emerges from something far more fundamental. This idea, known as emergent gravity, turns our intuition on its head. We are used to thinking of gravity as a force that acts within space and time. But what if space, time, and gravity are all collective phenomena, like the temperature of a gas or the wetness of water? Temperature is not a property of a single molecule. You cannot point to one air molecule and ask for its temperature. It is a statistical property that only makes sense when you have a vast number of molecules moving around. In the same way, emergent gravity proposes that the smooth, continuous fabric of spacetime and the curvature we call gravity are not basic building blocks. They arise from the chaotic interactions of countless tiny quantum bits of information. One of the most provocative versions of this idea comes from physicist Eric Verland. In 2010, he proposed a theory of entropic gravity. He started with the holographic principle, which tells us that information about a volume of space is stored on its boundary. Now think about entropy, which is often described as disorder, but is more precisely a measure of hidden information. Verland asked a simple, revolutionary question. What if gravity is not a fundamental force, but a consequence of nature's tendency to maximize entropy? Imagine a single particle sitting in space. According to Verland's math, when you bring a second particle near it, the holographic screen encoding the universe's information must rearrange itself to account for the new configuration. This reorganization, this drive toward higher entropy, manifests as an attractive force between the particles. Astonishingly, from this purely informational and thermodynamic starting point, Verland's equations naturally produce Newton's law of universal gravitation. It is as if gravity is not pulling objects together, but is rather the universe's way of staying as disordered and information-rich as possible. The implications are staggering. First, it offers a potential bridge between the quantum world and gravity, a problem that has vexed physicists for a century, by suggesting gravity is not a quantum force at all, but a statistical one. Second, and more controversially, Verland later extended his idea to suggest it could eliminate the need for dark matter. In his framework, the extra gravitational pull observed in galaxies is not caused by invisible matter, but is an emergent effect due to the way entropy and information behave on cosmic scales. The gravity we feel in the serene outskirts of a spiral galaxy would be subtly different, stronger, than what Newton or Einstein predict, simply because of how the quantum information on the galactic boundary is structured. While still highly speculative and debated, emergent gravity represents a profound shift in perspective. It asks us to consider that the most familiar force in our daily lives, the one that keeps our feet on the ground, might be a side effect, a mirage created by the hidden churn of cosmic information. The stage is not set before the play begins. The actors, through their collective performance, are creating the stage itself, moment by moment. The idea that gravity emerges from information paints a radically new picture, but it leaves a colossal question unanswered. Where is all the dark energy coming from? A seventh, startlingly elegant theory proposes an answer, and it points to the darkest objects we know. Imagine if the very expansion of the universe, the engine of dark energy, was not a property of empty space, but was instead being powered by black holes. This is the theory of cosmological coupling. For decades, we have understood that black holes grow by two methods. They can accrete matter, swallowing gas, dust, and stars that stray too close. They can also merge with other black holes. Their mass was thought to be locked, a final tally of what fell in. But a groundbreaking study published in 2022 examined ancient, dormant supermassive black holes at the hearts of galaxies across billions of years. By comparing the masses of these black holes in the young, distant universe to those in the older, nearer universe, astronomers found something impossible under the old rules. The black holes in the ancient universe were far too massive. They were 7 to 20 times larger than they should have been, given how much time they had to grow by normal accretion alone. The only way to explain their enormous size, the researchers proposed, is if the black holes are gaining mass from the expansion of the universe itself. Think of it this way: picture a rubber sheet representing space with a heavy weight representing a black hole. As you stretch the rubber sheet, the universe expanding, what happens to the weight? In Einstein's general relativity, mass and energy are two sides of the same coin. The theory of cosmological coupling suggests that as space stretches, the black hole's energy, and therefore its mass, increases in tandem. It is cosmically coupled to the expansion. Now, here is the breathtaking part. In Einstein's equations, this process works both ways. If the black hole's mass increases because of the expansion, then the black hole's presence also contributes to the expansion. It creates a feedback loop. The mathematics show that this contribution from black holes behaves exactly like a cosmological constant. It looks, for all intents and purposes, like dark energy. In this theory, dark energy is not a mysterious energy of the vacuum. It is the gravitational energy of black holes, harvested from the stretching cosmos and then given back to drive that stretching further. It is an elegantly closed loop. Black holes, formed from the collapse of massive stars in the early universe, become cosmic batteries. They store the energy of expansion, and then their coupled growth pumps that energy back into the fabric of space, accelerating the expansion we see today. This would solve two profound mysteries at once. It explains the source of dark energy, and it explains why supermassive black holes were so inexplicably large in the ancient cosmos. The darkness at the heart of every galaxy might not just be a consequence of the universe's story. It might be the hidden author writing the final chapters with its own growing gravitational influence. Black holes may be cosmic batteries, but their power is still channeled through the force of gravity, one of the four pillars of our reality. Yet a growing suspicion haunts the edges of physics, the idea that our cosmic inventory is incomplete. We have gravity, electromagnetism, and the strong and weak nuclear forces. These four fundamental interactions explain everything from the orbit of planets to the glow of a star. But what if there is a fifth force, a hidden hand subtly tugging at the universe? This eighth theory, the search for a fifth force, is not a fringe idea. It is a serious, methodical hunt for a crack in the standard model of particle physics. The motivation is compelling. We know dark matter exists, yet it seems to ignore three of the four forces entirely. It does not emit, absorb, or reflect light, so it ignores electromagnetism. It does not seem to be built from protons and neutrons bound by the strong force. It barely interacts with anything except through gravity. How can something so abundant be so aloof? The answer might be that dark matter does interact, but through its own private channel, a force carrier we have not yet detected. Enter the dark photon. In our familiar world, the photon is the particle of light, the messenger of the electromagnetic force. A dark photon is its hypothetical, shadowy counterpart. It would be the carrier of a new force, one that operates exclusively within the dark sector, a hidden realm of particles that includes dark matter. Think of it like two separate radio stations broadcasting in the same city. One station uses frequency A, and your regular radio can pick it up. That is the photon and our normal matter. The other station uses frequency B, which your radio is deaf to. That is the dark photon and dark matter, but under very specific conditions, a tiny bit of static might bleed through. If a dark photon has even a minuscule mixing with a regular photon, it could create a faint, detectable bridge between our world and the dark one. This possibility has sparked a global treasure hunt. Deep underground, in abandoned mines and beneath mountains, physicists have built exquisitely sensitive experiments to escape the cosmic ray noise of the surface. They use powerful magnets and supercooled detectors, waiting for a telltale flicker of energy that cannot be explained by any known particle. At facilities like CERN, scientists are not just smashing protons together. They are aiming particle beams at solid targets, searching for instances where a regular photon might briefly oscillate into a dark photon and then back again, leaving a missing energy signature in the detectors. Other experiments look for subtle anomalies in the behavior of electrons or muons, tiny deviations from predicted magnetic strengths that could be influenced by an unseen fifth force. Finding the dark photon would be a revelation on par with the discovery of the electron. It would not just be a new particle. It would be our first key to the dark sector, a Rosetta Stone allowing us to begin translating the language of the universe's hidden majority. It would prove that the cosmos is governed by a richer, more complex set of rules than we ever imagined, with forces operating in parallel to our own, invisible yet omnipresent. The silence in our detectors is not emptiness. It is the sound of physicists listening intently at a closed door, hoping to hear the faintest whisper from the other side. That hunt for a fifth force often assumes a constant, unchanging rule. But what if the hidden hand is not constant at all? What if it is a shape-shifter, a cosmic trickster that changes its very nature depending on where you look? This brings us to the ninth theory, the chameleon field, a brilliantly clever idea designed to solve the dark energy puzzle. Unlike the cosmological constant, which is a fixed property of space, the chameleon is a theoretical particle and its associated field that permeates the universe. Its defining, bizarre trait is right there in the name. Its mass is not fixed. In the dense, crowded environment of our planet, surrounded by atoms and molecules, the chameleon field would have an extremely large mass. This is crucial because in particle physics, a large mass means a very short range. The field's influence would be limited to microscopic distances, effectively shutting itself off and hiding from our most sensitive laboratory experiments. It blends into the background like a chameleon matching the color of a leafy branch. But now follow that field out into the deep cosmos, between galaxies where the average density of matter is less than a single atom per cubic meter. The environment is almost a perfect vacuum. In this incredible emptiness, the chameleon field's mass would become vanishingly small, and a particle with a very small mass can exert its influence over colossal cosmological distances. In this state, the chameleon field would produce a long-range repulsive force, pushing space itself apart and driving the accelerated expansion we attribute to dark energy. It is a single, elegant entity that behaves one way here on Earth to avoid detection, and in an entirely different way out in the void to shape the fate of the universe. To picture this, imagine a spring. In a crowded box full of other objects, the spring is compressed tightly, its energy confined and its push limited to a tiny space. That is the chameleon on Earth. Now place that same spring in an empty, vast warehouse. It can fully extend, releasing its energy across the entire room. That is the chameleon in interstellar space. This theory is not just mathematical speculation, it makes testable predictions. If a chameleon field exists, it would cause a slight, additional force between masses in a vacuum, a deviation from pure Newtonian gravity that could be spotted in exquisitely precise experiments. Some searchers have used ultra-cold atoms in vacuum chambers, watching how they fall under gravity, looking for any whisper of an extra push or pull. Others propose using neutron stars, the incredibly dense cores of dead stars, as natural laboratories. The intense gravity of a neutron star creates an extremely high-density environment right next to the near vacuum of space, a perfect place to look for a force that changes strength across a short distance. While no confirmed detection has been made, the chameleon remains a compelling candidate. It represents a different kind of thinking, where the hidden force of the cosmos is not a passive background energy, but an active, responsive entity that literally feels the texture of the universe around it and changes its costume accordingly. The emptiness of space might not be empty of influence. It might simply be the only place where this shyest of cosmic actors feels free to reveal its true, universe-altering power. The chameleon field hides in plain sight, but some cosmic secrets are written across the entire sky for anyone to see if they know how to look. Our 10th theory confronts a pattern so unsettling that scientists gave it a dramatic name, the axis of evil. This is not a galactic superweapon, but a bizarre and controversial alignment etched into the oldest light in existence, the cosmic microwave background. This faint afterglow, a snapshot of the universe when it was just 380,000 years old, should be the very picture of uniformity. The Big Bang Theory, bolstered by cosmic inflation, predicts this radiation should be almost perfectly isotropic, meaning it should look the same in every direction, with only tiny, random fluctuations from place to place. For the most part, it does, but when scientists created exquisitely detailed maps of this microwave sky, they noticed something strange. The largest scale fluctuations, the hot and cold spots stretching across billions of light years, are not randomly scattered. They appear to align along a particular axis, a preferred direction in space. Even more bizarrely, this axis seems to be eerily aligned with the plane of our own solar system and the direction of the Earth's motion through the cosmos. This is deeply troubling. It is as if the fossilized imprint of the infant universe somehow knows about our local, modern-day neighborhood, a connection that should be cosmologically impossible. The statistical significance of this alignment is debated. hovering at a level that is too strong to easily dismiss as a fluke, yet not strong enough to definitively declare a crisis. The name Axis of Evil, coined half-jokingly, reflects how this anomaly evil lie undermines a cornerstone of modern cosmology, the cosmological principle, which states the universe is homogeneous and isotropic on large scales. No matter where you are, the universe should look roughly the same. A preferred axis shatters that assumption, so what could possibly explain it? One radical possibility is that the universe has a non-trivial topology. Imagine our cosmos is not infinite but finite and shaped like a hall of mirrors, perhaps a twisted donut shape on a scale so vast we see its repeating patterns as ghostly alignments. Another idea points to primordial magnetic fields, vast structures woven into the fabric of space before the first stars formed, that could have stretched and oriented the early plasma, leaving a directional stamp on the light. There are also more sober, if unsettling, suggestions. Perhaps it is a statistical illusion, a cruel trick of the data, or perhaps our measurements are contaminated by something far closer to home, an unknown foreground emission from our own galaxy that we have not yet perfectly subtracted from the maps. Yet after years of analysis and new data from satellites like Planck, the anomaly stubbornly persists. For many cosmologists, it is a persistent itch at the back of the mind. It is the possibility that our magnificent, inflation-smoothed universe might bear a faint scar from something that came before the Big Bang, or a fingerprint of a deeper layer of reality that breaks the rules we hold most sacred. The axis of evil may not be malevolent, but its silent presence in the cosmic background is a constant, quiet challenge. A reminder that the universe's first light might still be holding onto secrets we have only begun to decipher. The axis of evil suggests a cosmic structure we cannot see, but our own galaxy is caught in a river of motion we cannot fully explain. On the grandest scales, galaxies are not simply drifting apart with the universe's expansion. They are also streaming, flowing together in vast, coherent rivers hundreds of millions of light-years across. This is a bulk flow, and tracing its source leads to one of the most profound gravitational mysteries in our cosmic backyard. For decades, astronomers have known that our Milky Way, along with our entire local group of galaxies and the immense Virgo supercluster it belongs to, is hurtling through space at a staggering speed of over 600 kilometers per second. We are not just expanding, we are being pulled. The prime suspect for this cosmic tug is known as the Great Attractor. This is not a single object, but a colossal gravitational anomaly, a concentration of mass equivalent to tens of thousands of Milky Ways, located roughly 250 million light-years away in the direction of the constellations Centaurus and Hydra. There is a major problem, however. This region lies almost directly behind the plane of our own galaxy, an area astronomers call the zone of avoidance. The dense gas, dust, and stars of the Milky Way's disk blot out visible light from beyond, creating a blind spot that hides the Great Attractor from our direct view. It is like trying to find a distant mountain range while staring directly into a fog bank. We can only infer its presence by observing its gravitational pull on everything around it, mapping how thousands of galaxies are being drawn toward this one point in the sky. But the story grows even stranger. Recent, more precise mapping of these cosmic flows has revealed that the Great Attractor alone cannot account for our motion. To explain the full speed and direction of our galactic journey, scientists had to propose an even more enigmatic counterpart: meet the dipole repeller. While the Great Attractor pulls us, the dipole repeller is theorized to push us. It is not a repulsive force in the traditional sense, but rather a vast, underdense region of space, a cosmic void of staggering proportions. In the gravitational tug-of-war of the universe, an area with far less matter than average exerts less pull, surrounded by regions of higher density that pull more strongly from the opposite direction. This void effectively creates a push. Imagine you are in a crowded swimming pool and everyone is holding hands in a giant circle. If one side of the circle suddenly has many fewer people, the collective pull from the crowded side would draw you toward it, making it feel as if the empty side was pushing you away. The dipole repeller is that empty side on a cosmic scale. It is a place where the cosmic web of galaxies has left a gaping hole, a desert of near-nothingness that shapes the motion of entire superclusters. Together, these two titans, one an unseen concentration of mass and the other an unimaginable emptiness, define the largest gravitational landscape we have ever mapped. They suggest the universe's structure is governed by imbalances we are only beginning to chart, with dark matter likely weaving the dense knots of the great attractor and leaving the voids of the repeller startlingly bare. Our place in the cosmos is not a still point, but a journey along a gravity river, flowing between a hidden mountain and a silent, expansive sea of nothing. This cosmic river of galaxies flows according to the rules of gravity, but at the edge of a black hole, those rules break down completely. The black hole information paradox is not just a puzzle, it is a screaming contradiction at the heart of physics, a battle between our two most successful theories over the universe's most sacred law. On one side stands quantum mechanics, which governs the very small. Its core principle is unitarity, the idea that information is never lost. You can burn a book, but in principle, if you could collect every single ash particle and trace every photon of light and heat emitted, you could reconstruct the entire text. The information is scrambled, but it still exists in the universe. On the other side stands Einstein's general relativity, which governs gravity and the very large. It describes black holes as objects with an event horizon, a point of no return. Anything that crosses this boundary, whether a spaceship, a star, or a book, is lost forever to the outside universe. The information it carried is gone, erased from our cosmic ledger. For decades, physicists accepted this grim fate until Stephen Hawking made a shocking calculation. He showed that black holes are not perfectly black. Due to quantum effects near the event horizon, they slowly evaporate, emitting a faint glow we now call Hawking radiation. This radiation, however, is purely thermal, like the heat from a stove. It carries no information about what fell in. So, imagine our book falls into a black hole. The black hole eventually evaporates away entirely, leaving behind only this featureless thermal radiation. The information in the book is gone, violating quantum mechanics. This is the paradox. For 50 years, it has been physics' most vexing problem. A proposed solution led to an even more disturbing idea, the firewall paradox. If information must somehow escape the black hole, perhaps it does so in a violent last burst as the black hole nears the end of its life. But for that to work, the event horizon could not be the smooth, empty space Einstein predicted. Instead, it would have to be a searing wall of high-energy particles, a firewall that would incinerate anything trying to cross. This violates general relativity, which says you should notice nothing special as you cross the horizon. We are left with an impossible choice. Either information is destroyed or astronauts are burned alive by a lawless barrier. Modern physics has rallied around a more elegant escape route, one that returns us to the holographic principle. The key insight is that the information never actually falls into the black hole in the way we think. Remember, the holographic principle states all information within a volume is encoded on its boundary. For a black hole, that boundary is the event horizon. When the book falls toward the black hole, its information is not carried inward. Instead, it is smeared and encoded onto the chaotic, boiling quantum bits that make up the horizon's surface, like a message being etched onto a vast, hot plasma. The book itself passes through, but a perfect copy of its information remains plastered on the wall. Hawking radiation, then, is not random. It is the slow, meticulous process of this encoded information on the horizon being emitted back out into the universe, one quantum fragment at a time. The radiation only looks thermal and random until you have all the pieces of the puzzle. When you collect the final photon from the black hole's last gasp, you would have all the data needed to reconstruct the original book. The most recent and mind-bending development in this saga is the concept of island universes. This idea suggests that as the black hole evaporates, regions inside the event horizon, deep within the black hole itself, can become entangled with the radiation escaping far outside. These interior regions, called islands, effectively become part of the external universe's information storage system. It is as if the universe, to protect its informational integrity, can reach back in time and space to rescue data from behind the veil of darkness. The black hole information paradox is more than a technical debate. It is a struggle for the soul of physical law, forcing us to choose between the permanence of information and the smoothness of spacetime. The resolution points toward a universe where nothing is ever truly lost, only transformed and hidden in the most unexpected places, written on the walls of oblivion itself. The paradox of information suggests reality has rules written in code, but what if the code itself is the only reality? Our 13th theory is perhaps the most provocative of all, the simulation hypothesis. It proposes that our entire universe, from the farthest galaxy to the feeling of sunlight on your skin, is not base reality, but an incredibly sophisticated simulation, a cosmic video game run by a civilization vastly more advanced than our own. This is not just science fiction. Philosopher Nick Bostrom formalized the argument as a stark trilemma. He posits that at least one of three statements must be true. First, that almost all civilizations at our level go extinct before becoming technologically mature. Second, that almost all mature civilizations lose interest in creating simulated realities. Or third, that we are almost certainly living in a simulation. The logic is statistical. If even one civilization survives to a post-human stage and has even a modest desire to run ancestor simulations, recreating their own past or exploring history, they would have the computational power to generate a staggering number of such simulations. The number of simulated minds would vastly outnumber the biological ones. Therefore, if you are a conscious being, the odds are overwhelming that you are in one of the countless simulations, not in the original biological reality. The argument hinges on the assumption that consciousness is substrate independent, that it can arise from the right kind of information processing, whether in a brain or in a supercomputer. If that is true, then simulated beings would be as real to themselves as we are to us. From a scientific perspective, some researchers suggest we might look for evidence of the simulation in the very fabric of physics. All simulations, no matter how advanced, require finite resources. There would be limits to resolution and processing power. One potential glitch could be found in the behavior of cosmic rays. These high-energy particles from deep space smash into our atmosphere, creating cascades of secondary particles. In a simulated universe, the laws of physics are computed on a discrete lattice, a fundamental grid of spacetime pixels. If such a grid exists, there would be a preferred direction, breaking the perfect symmetry we expect. Some physicists have proposed that if we see certain patterns or anomalies in the distribution of these cosmic rays, it could hint at the underlying lattice structure of our simulated reality. Another place to look is in the bizarre rules of quantum mechanics, the famous double-slit experiment where a single particle seems to pass through two holes at once, only deciding on a definite path when we observe it, has long felt like a program optimizing its processing. Why does the universe only calculate the precise details of a system when someone is looking? It is eerily reminiscent of a video game engine that only renders the graphics in the player's immediate field of view to save computational resources. The simulation hypothesis also provides a chillingly elegant answer to the fine-tuning problem. Why are the fundamental constants of nature so perfectly calibrated to allow for stars, planets, and life? In a simulated reality, the parameters are simply set that way by the programmers, perhaps as part of an experiment or a form of entertainment. the theory is impossible to definitively prove or disprove from within the system, which is why many scientists dismiss it as unfalsifiable metaphysics. Yet it persists as a powerful thought experiment, forcing us to confront the nature of reality itself. If we are in a simulation, then the hidden forces we have been exploring, from dark energy to quantum fields, are not laws of nature, but the underlying algorithms of the simulation, the source code of our existence. Every strange quantum effect, every cosmic coincidence, becomes a potential clue that we are living in someone else's grand and possibly forgotten experiment. The simulation hypothesis asks if our universe is a programmed construct, but a 14th theory offers a different kind of creation story, one without a beginning or an end. The ekpyrotic and cyclic universe models propose that our Big Bang was not a singular, explosive birth from nothing, but a violent collision in a higher dimensional space. This idea emerges from the landscape of string theory, which suggests our three-dimensional universe might be a membrane, or brain for short, floating in a space with more dimensions than we can perceive. Picture our entire cosmos as a vast, flat sheet, like a page of an unimaginably large book. Now, imagine another such sheet, another brain, floating parallel to ours in this higher dimensional bulk. In the cyclic model, these two brains are drawn together over eons by a hidden force, perhaps a form of dark energy operating in the extra dimensions. They move on a cosmic timescale, slowly, inevitably, until they collide. That collision is our Big Bang. The immense kinetic energy of the impact is converted into the searing heat, radiation, and matter that filled our newborn universe. There is no singularity, no point of infinite density where the laws of physics break down. Instead, there is a transfer of energy between two physical objects in a larger reality, a cosmic car crash of breathtaking scale. After the collision, the brains bounce apart, filled with the debris of the impact, which expands and cools to form the galaxies and cosmic microwave background we see today. But the story does not end there. As the brains fly apart, the hidden force between them once again becomes attractive, gently pulling them back together over trillions of years. The universe expands, grows cold and dark, its stars long dead, but the approach of the other brain slowly drains energy from our own, causing a gradual contraction just before the next collision. This sets the stage for an endless cycle, a cosmic heartbeat of creation, expansion, cooling, and rebirth. This model elegantly explains the uniformity of the cosmic microwave background. Before the collision, the two brains are flat and smooth, stretched taut over cosmic distances. When they meet, that smoothness is imprinted on the newborn universe, creating the nearly identical temperature we see in all directions without requiring a separate period of hyper-fast inflation. It also offers a profound answer to the question of what came before the Big Bang. There was always a before, an endless sequence of universes, each with its own laws and constants potentially reset by the violence of the collision. Our existence is just one chapter in an infinite cyclical epic, a universe born from the ashes of its predecessor, destined to die and give rise to the next. The hidden force driving the brains together is the true engine of eternity, a silent, dimensional tug that ensures the cosmos never truly ends, only transforms in a perpetual dance of destruction and creation. The endless cosmic cycle of brains suggests a deeper, unified layer of reality, a single set of rules from which all diversity springs. This brings us to the 15th theory, the monumental quest for a theory of everything. For over a century, physics has been split into two magnificent but incompatible kingdoms. General relativity masterfully describes the force of gravity and the cosmos on the largest scales, painting a picture of curved spacetime and cosmic evolution. Quantum field theory, with breathtaking precision, governs the other three forces, electromagnetism and the nuclear forces, explaining the chaotic dance of particles on the smallest scales. Each is spectacularly successful in its own domain, but when forced to meet, they produce nonsense, predicting infinities at places like the center of a black hole or the moment of the Big Bang. The dream of a theory of everything is to find the underlying framework, the single equation or principle from which both gravity and quantum mechanics naturally emerge like different facets of the same gem. The most famous and controversial candidate for this unified theory is string theory. Its core idea is radical simplicity. It proposes that the fundamental constituents of the universe are not zero-dimensional point particles like dots on a page. Instead, they are unimaginably tiny, one-dimensional loops or strands of pure energy, vibrating strings. Just as different vibrations on a violin string produce different musical notes, the distinct vibrational patterns of these fundamental strings give rise to the different properties of all the particles we see. One specific resonance might be an electron, another a quark, and another might be the particle that carries the gravitational force, the graviton. This elegant idea immediately solves the fatal clash between gravity and quantum mechanics by banishing the problematic point like singularity. A string has a finite size, smoothing out the infinities that plague other theories. But this beautiful solution comes at a staggering cost: extra dimensions. For the math of string theory to work consistently, it requires not the 3 spatial dimensions we experience, but 10, or in its most advanced form, 11. Where are these extra dimensions? The theory suggests they are compactified, curled up into a space so fantastically small at the Planck scale that they are completely hidden from our perception. To understand this, picture a garden hose. From a great distance, it looks like a one-dimensional line. But if you could shrink down to the size of an ant and crawl on its surface, you would discover it has a second dimension, a circular direction that loops around the hose's circumference. Our universe, according to string theory, might be like that, with 6 or 7 extra dimensions curled up at every single point in space, shapes known as Calabi-Yau manifolds, whose intricate geometry determines the laws of physics in our visible 3-dimensional world. This leads to the theory's most profound and troubling implication: the landscape. The way these extra dimensions curl is not unique. String theory allows for a truly astronomical number of possible stable configurations, perhaps 10 to the power of 500. Each configuration corresponds to a different vacuum state, a universe with its own distinct set of physical constants and laws. Our universe, with its specific electron mass and gravitational strength, would be just one possibility in a vast, hidden archipelago of realities. This landscape provides a potential home for the multiverse we discussed earlier, but it also presents the theory's greatest challenge: testability. If the energy scales required to see strings or uncurl extra dimensions are a quadrillion times beyond the reach of any conceivable particle accelerator, how can we ever prove it? Some hope lies in finding relics from the early universe, like specific patterns in gravitational waves from cosmic inflation, or in discovering supersymmetric particles at facilities like the Large Hadron Collider, a key prediction of many string theories. Yet for now, it remains a majestic and untested mathematical edifice. String theory is less a single theory and more a vast web of interconnected possibilities, a framework suggesting that the most basic ingredients of reality are not things but tiny, vibrating threads of energy, weaving the fabric of everything we know from the hidden depths of a higher dimensional space. String theory's landscape of possibilities leads us to a haunting question about our own place in the cosmos. Why does the universe seem tailor-made for our existence? The values of the fundamental constants, like the strength of gravity or the mass of an electron, appear to be fine-tuned with impossible precision. If gravity were just a fraction stronger, stars would burn out in a cosmic flash, leaving no time for planets to form or life to evolve. If the nuclear forces were slightly weaker, hydrogen would never fuse into helium, and the universe would be a dark, empty sea of the simplest element. This eerie calibration is the heart of the 16th theory, the anthropic principle. It is not a force or a particle, but a logical framework for confronting the universe's apparent design. The weak anthropic principle states a simple, almost obvious truth. We can only observe a universe that is compatible with our existence as observers. If the constants were different, we would not be here to notice. It is a selection effect, like a lottery winner marveling at their own luck without considering all the losing tickets. The strong anthropic principle goes much further. It suggests the universe must have properties that allow life to arise at some point in its history. This stronger version edges into philosophical territory, hinting that the existence of conscious observers is not a happy accident, but a necessary feature of reality itself. The debate over fine-tuning is one of the most profound in science. For some, it is the most compelling evidence for a hidden designer, a cosmic architect who set the dials just right. For others, it is a statistical puzzle solved by the multiverse. In an infinite ensemble of universes, each with randomly different constants, it is inevitable that a few will, by pure chance, have the perfect conditions for life. We simply find ourselves in one of those lucky few. There is no design, only a colossal cosmic lottery where our number happened to come up. This idea connects directly to the landscape of string theory and eternal inflation. Every bubble universe in that frothing multiverse could have a different set of physical laws determined by how its extra dimensions curled. In this view, fine-tuning loses its mystery. With an infinite number of tries, a life-permitting universe is not just possible, it is guaranteed. The anthropic principle, therefore, sits at a crossroads between physics and philosophy. It forces us to ask whether the hidden forces we have catalogued are the result of a deep, underlying necessity, a breathtaking coincidence, or the signature of a reality so vast that every possible configuration of existence is playing out somewhere in the hidden dark. The fine-tuning of our universe suggests a cosmos built for connection, but at the quantum level, that connection becomes something far more intimate and instantaneous. Two particles can be created together, then separated by the width of a galaxy. Yet, if you measure the property of one, like its spin, the other particle's spin instantly snaps into a corresponding state, no matter the distance. This is quantum entanglement, a phenomenon so bizarre Einstein famously dismissed it as spooky action at a distance. He believed it revealed a flaw in quantum theory, assuming there must be hidden variables, unseen properties predetermined at the moment of separation that would explain the correlation without any faster-than-light communication. For decades, it remained a philosophical debate until physicist John Bell devised a mathematical test. Bell's theorem showed that if hidden variables existed, the correlations between entangled particles would have a strict upper limit. Quantum mechanics predicted correlations that would exceed this limit, a clear fork in the road. When experiments were finally performed, the results were unequivocal. The quantum predictions were correct. There are no hidden variables. The particles are genuinely connected in a way that transcends space. It is not a signal traveling between them. It is as if they are two sides of a single coin, and flipping one side instantly determines the state of the other, even if that coin is split across the universe. This non-locality is a fundamental feature of reality, a hidden force of correlation that operates outside our everyday notions of cause and effect. But the deepest mystery is what this entanglement might be building. A radical theory gaining traction suggests that spacetime itself, the very stage of the cosmos, might not be fundamental. Instead, it could emerge from a vast underlying network of quantum entanglement. Picture the universe as a cosmic fabric. In this view, the threads of that fabric are not tiny strings of energy, but trillions upon trillions of entangled quantum bonds. Where entanglement is dense and complex, it creates the geometry of space and the flow of time. Where it is sparse or absent, you get separation and distance. In a sense, gravity might be a side effect of this quantum information trying to maximize its entanglement connections. This idea turns our understanding inside out. We think of particles existing within space and becoming entangled. But what if entanglement comes first? What if particles are only connected because they are manifestations of a deeper, entangled web, and our perception of space is just a useful map of those connections? It implies that the spooky action Einstein disliked is not a bug in the universe's programming, but the source code. The hidden force weaving everything together is not a force at all, but a silent, instantaneous correlation, a cosmic glue from which distance and perhaps even reality itself is spun. Quantum entanglement weaves a hidden web of connection, but can we actually feel the raw energy of the quantum vacuum? The answer is yes, and we have measured it. The Casimir effect is a laboratory-sized whisper of the universe's deepest hidden force, a direct tug from the seething sea of virtual particles. Picture two perfectly smooth, uncharged metal plates placed parallel to each other in an absolute vacuum, separated by a gap smaller than the width of a human hair. According to classical physics, nothing should happen, but in our quantum reality, something extraordinary does. The plates are pushed together by an invisible pressure. This force arises from the zero-point energy fluctuations we discussed earlier. In the empty space outside the plates, virtual particle pairs of all wavelengths can blink in and out of existence. But in the narrow gap between the plates, only certain wavelengths can fit, much like how only specific musical notes resonate in a pipe of a given length. This restriction means there are slightly fewer possible quantum fluctuations between the plates than outside them. The relentless pressure from the more crowded sea of virtual particles on the outer sides overwhelms the weaker activity in the gap, pushing the plates together. It is a physical, measurable proof that empty space is not empty. It is a dynamic medium brimming with transient energy. This confirmed phenomenon gives startling credibility to the concept of negative energy densities. In certain quantum configurations, like the precise arrangement of these plates, the energy density between them can be calculated to be lower than the energy density of the pure vacuum outside. In a sense, it dips below what we call zero, creating a region of negative energy. While this is a tiny, localized effect, it opens a door to theoretical possibilities that sound like pure science fiction. The equations of general relativity allow for the existence of traversable wormholes, shortcuts through spacetime, and even warp drives, engines that could contract space in front of a ship and expand it behind. But these structures have a catch. They require exotic matter with negative energy density to hold them open and prevent collapse. For decades, this was seen as a definitive barrier, as negative energy seemed like a mathematical fantasy. The Casimir effect changes that. It demonstrates that negative energy densities, while minuscule, are a real feature of quantum field theory. The immense challenge, of course, is scale. The Casimir force we measure is incredibly weak. To stabilize a wormhole large enough for a proton to pass through might require negative energy equivalent to compressing the mass of Jupiter into a microscopic region. Current technology is nowhere close, but the principle is no longer completely forbidden by physics. The vacuum itself provides the blueprint. This means the hidden force that pushes two metal plates together in a lab might, in some distant future, be the same hidden force that engineers spacetime, bending the universe to our will not by brute strength, but by cleverly manipulating the ghostly energy of nothingness itself. The Casimir effect shows us the vacuum can be tamed, but another ghost from the early universe has eluded capture for over a century. Every magnet you have ever held, from a simple refrigerator decoration to the compass in your phone, has two inseparable poles, a north and a south. Break a magnet in half and you do not get an isolated north or south. You simply create two smaller magnets, each with its own pair of poles. This duality seems as fundamental as nature gets. Yet our most ambitious theories of physics insist it should not be this way. They predict the existence of a magnetic monopole, a hypothetical particle that carries only a single magnetic charge, either a north or a south, with no opposite partner. Think of electric charge. You can have a positive proton or a negative electron existing completely independently. Grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces into a single framework, demand that magnetism should have this same property. In the unimaginable heat of the first fractions of a second after the Big Bang, these forces were one. As the universe expanded and cooled, they split apart in a series of phase transitions, much like water freezing into ice crystals. And just as freezing water can trap bubbles or create cracks, that cosmic phase transition should have created topological defects, knots in the fabric of spacetime that manifest as monstrously heavy, stable particles, magnetic monopoles. According to these theories, they should be as common as protons. We should be swimming in them. The fact that we are not, that not a single magnetic monopole has ever been conclusively observed, is one of the most glaring discrepancies between prediction and reality. This is the magnetic monopole problem. Their absence posed such a crisis that it became a key motivation for the theory of cosmic inflation. The idea was that the hyper-fast expansion of the infant universe would have diluted these primordial relics to such an extent that there might be only one in our entire observable cosmos, effectively rendering them invisible. But that solution feels almost too convenient. The hunt has not stopped, because monopoles would be so massive, perhaps a quadrillion times heavier than a proton, and carry such a powerful magnetic charge, they would leave an unmistakable signature. They would ionize matter as they pass through it, like a cosmic lightning bolt tearing through atoms. Experiments have searched for decades. Some use vast arrays of sensors deep in abandoned mines, shielded from cosmic rays, waiting for the telltale trail of a monopole lumbering through the Earth. Others repurpose particle detectors like those at the Large Hadron Collider, hoping to create one in a collision, though the energies required are likely far beyond our reach. The most poetic searches look not underground, but in the most ancient material we can find, samples of moon rock or in the crystalline structure of ancient mica. The logic is that a monopole passing through such material over billions of years would leave a permanent, etched damage trail that we could now find with a microscope. Finding a magnetic monopole would be a discovery of Nobel Prize magnitude. It would be a direct fossil from the universe's first moments of symmetry breaking, a tangible piece of evidence for grand unification. Its continued absence, however, is a silent, persistent reminder. It tells us that our most elegant theories of hidden forces, while powerful, are still missing a crucial piece of the cosmic puzzle, a piece that may be hiding in plain sight or lost in the vast emptiness between the stars. The magnetic monopole remains a ghost from the first moments of symmetry, but sometimes a hidden force reveals itself as a gentle, persistent push against our expectations. In the vast quiet of the outer solar system, two robotic pioneers carried a secret. The Pioneer 10 and Pioneer 11 spacecraft, after their missions to Jupiter and Saturn, continued coasting toward interstellar space. For years, scientists meticulously tracked their trajectories using the Deep Space Network, and they noticed something deeply puzzling. Both spacecraft were experiencing a tiny, constant sunward deceleration. It was an anomaly so small, about 10 billion times weaker than the gravity we feel on Earth, but it was there, an unexplained drag acting on the probes as they sailed into the black. This was the Pioneer anomaly. For over a decade, it fueled speculation about a breakdown of Newton's laws at great distances, or perhaps an unknown, long-range force emanating from the Sun, a subtle whisper of modified gravity. The mystery captivated physicists, offering a potential solar system-sized laboratory to test our understanding of hidden forces. The solution, when it finally arrived, was both elegant and humbling. Through painstaking analysis of decades-old engineering data and new thermal modeling, researchers determined the culprit was not a new force of nature but an old one, heat. The spacecraft were powered by radioactive thermoelectric generators, and the faint but constant infrared radiation emitted from their warm surfaces acted like a tiny, braking photon rocket. The heat was not perfectly symmetric, and this minuscule anisotropic radiation provided just enough push to account for the anomaly. The case was largely closed. Yet the legacy of the Pioneer anomaly is far more important than its resolution. It stands as a masterclass in scientific vigilance, demonstrating how the tiniest discrepancy, a drift no greater than the acceleration of a car coasting to a stop over 100 miles, can ignite a profound search for new physics. It reminds us that our solar system might still hold other, subtler anomalies. For instance, the precise orbits of some distant trans-Neptunian objects show slight clustering that a few astronomers suggest could hint at the gravitational influence of a still unseen Planet 9, a massive body lurking in the frozen dark. Others look at the flyby anomalies where spacecraft like Galileo and near Shoemaker experienced unexpected, tiny velocity changes during Earth gravity assist maneuvers, changes that standard models could not fully explain. Each of these minute deviations is a potential crack in the edifice. Could they be statistical flukes or complex modeling errors like the thermal radiation explanation for Pioneer? Almost certainly, but the possibility remains that one of them might be real, a signal of something deeper. They fuel the fire for theories of modified gravity, like MUND, suggesting that the extremely weak gravitational environment in the outer solar system might be where Newtonian dynamics begins to subtly fail. Or they could point to an unknown interaction between mass and spin, or a fifth force with a range measured in astronomical units. These anomalies are the faintest of tremors in the fabric of our cosmic backyard. They teach us that hidden forces do not always announce themselves with the violence of a black hole or the grandeur of dark energy. Sometimes they are a barely perceptible tug, a quiet question whispered by a silent spacecraft as it leaves our home behind, urging us to look closer at the rules we think we know. These quiet anomalies in the solar system remind us that even the most basic aspects of our reality deserve scrutiny. Nothing feels more fundamental than the steady, forward march of time itself. We watch an egg shatter on the floor, steam rise from a cup, and a star burn out, all processes that never spontaneously reverse. This relentless directionality is called the arrow of time, and its origin is one of the deepest mysteries in physics. The conflict is stark and beautiful. The fundamental laws governing particles, from Newton's mechanics to Einstein's relativity and quantum theory, are almost perfectly time-symmetric. If you were to film two electrons colliding and then play the film backwards, the reversed motion would be just as valid according to the equations. There is no inherent past or future in the math. Yet, in the world we experience, time has a clear and irreversible direction. You never see scattered eggshells leap from the floor to reassemble into a whole egg in your hand. The key that breaks the symmetry is entropy, the measure of disorder or hidden information in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This is not a suggestion, it is a statistical certainty. A broken egg has more possible microscopic arrangements for its molecules than a neatly assembled one in a shell. The universe overwhelmingly tends toward states of higher probability, which are states of higher entropy. So the arrow of time, the feeling of past versus future, may not be written into the laws of motion themselves, but emerges from the statistical tendency of things to become more disordered. This leads to a profound question. Why was the entropy of the early universe so incredibly low? To have an arrow of time pointing forward for billions of years, the universe must have started in a state of exceptionally high order, a pristine, smooth, low-entropy configuration. This is the ultimate boundary condition, the true beginning that sets the direction for everything that follows. Some physicists propose that time itself, as a dimension we move through, might be an emergent property, not a fundamental one. Just as the concept of temperature emerges from the motion of many molecules, the flow of time could emerge from the changing quantum entanglement relationships between particles. In this view, what we perceive as the passage of time is really the universe updating its internal quantum correlations. A clock ticks not because of some universal metronome, but because the configuration of entanglement in the system we call a clock is evolving in a predictable way. This radical idea suggests that at the most fundamental level, perhaps in the domain of quantum gravity or a theory of everything, time does not exist. There is only a vast, timeless network of correlations. Our conscious experience of a flowing present is a story our brains construct from this static cosmic tapestry. Much like a single frame in a film strip only gains meaning when projected in sequence. We are embedded in the process, so we experience the sequence. The nature of time forces us to confront the core of our reality. Is the forward rush we feel every day a fundamental force of the cosmos, or is it the most personal and convincing illusion, emerging from a hidden, timeless order beneath the chaos? The relentless forward march of time grants us a history, and within that history lies a profound silence. Our galaxy, the Milky Way, is over 13 billion years old, contains hundreds of billions of stars and likely trillions of planets. Even if intelligent life is exceedingly rare, the sheer scale of time and space suggests that countless civilizations should have arisen long before us. They should have spread across the galaxy, leaving behind engineering projects on a cosmic scale, or at the very least filling the airwaves with signals. Yet we see nothing, we hear nothing, the universe appears starkly, hauntingly empty. This contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it is the Fermi paradox, named for physicist Enrico Fermi, who famously asked, "Where is everybody?" It implies a hidden force, not of physics but of fate, that actively suppresses the rise of visible, spacefaring civilizations. One compelling answer is the Great Filter theory. This idea proposes that the evolution of life from simple chemistry to a galaxy-spanning civilization is not a smooth, inevitable climb. Instead, it is an obstacle course with at least one step so improbably difficult, so lethal, that it acts as a cosmic bottleneck, filtering out almost everyone. The terrifying question is where this filter lies in the sequence. Is it behind us or ahead of us? If the Great Filter is in our past, it means we are miraculously rare. We have already passed the universe's most difficult test. Perhaps the jump from non-living chemistry to simple, self-replicating life is astronomically unlikely, a freak event that has only happened a handful of times in the entire galaxy. Or maybe the transition from single-celled life to complex, multicellular organisms is the true barrier. In this scenario, the silence of the cosmos is a sign of our incredible luck and solitude. We are the lonely winners of a cosmic lottery, and the galaxy is our untouched inheritance. The alternative is far more grim. The Great Filter could still lie in our future. This means the step from our current technological adolescence to a stable, interstellar species is the nearly impossible one. Every civilization that reaches our level of development may inevitably discover the technology that leads to its own destruction, whether through nuclear war, engineered pandemics, runaway artificial intelligence, or some other existential catastrophe we have not yet conceived. The silence, then, is a cemetery. It is the sound of countless civilizations flickering out just as they were about to announce themselves to the stars. There is a third, more unsettling possibility, that the filter is not a single event but a constant presence. Perhaps advanced civilizations do not die out, but simply lose interest in physical expansion or communication, retreating into immersive virtual realities or forms of existence we cannot detect. Or maybe they are out there, but they see us as we see an anthill, not worthy of contact or too primitive to notice. The Fermi paradox forces us to confront our own trajectory. Every new telescope that fails to find signs of engineering, every silent radio band, is a piece of data pointing toward the existence of this hidden filter. As we develop technologies capable of reshaping our world and our species, we are not just advancing scientifically, we are actively testing which side of the filter we are on. The greatest hidden force shaping the cosmic landscape may not be gravity or dark energy, but a simple, brutal law of probability that ensures the universe remains forever quiet, its potential forever unfulfilled. The profound silence of the cosmos might be a clue to our own improbable existence, but probability itself can lead to a truly terrifying conclusion. The Boltzmann brain paradox is a statistical nightmare that threatens to unravel our confidence in reality itself. It begins with a simple, undeniable fact of thermodynamics. In a system that lasts for an eternity, even the most unlikely fluctuations will eventually happen. Given enough time, a room full of gas molecules left to their chaotic dance will by pure chance momentarily arrange themselves into the shape of a perfect ice cube or a tiny sculpture or even a written sentence. Now apply this to the entire cosmos. If our universe is eternal or part of an eternal multiverse, then over infinite time, the random jostling of particles in the void could spontaneously assemble any configuration, no matter how complex. This includes a fully formed, self-aware human brain, complete with a lifetime of false memories floating alone in the darkness. According to raw probability, the spontaneous fluctuation of a single, conscious brain from the chaos is astronomically more likely than the gradual, ordered evolution of an entire 14 billion-year-old universe filled with galaxies, stars, planets, and billions of other brains. The math is brutally simple. It takes far fewer particles and far less specific organization to assemble one brain with fabricated experiences than to build the colossal, consistent structure we see around us. Therefore, if the universe is eternal and random, you should statistically be a Boltzmann brain, a momentary flicker of consciousness in an endless sea of disorder, rather than a person embedded in a vast, ancient cosmos. This is not just a philosophical puzzle. It is a direct assault on our cosmological models. If our best theories predict that Boltzmann brains are overwhelmingly more common than ordinary observers like us, then those theories are almost certainly wrong. We have direct evidence that we are not Boltzmann brains. We observe a coherent, law-abiding universe with a deep past recorded in starlight and fossils. Any theory that makes our existence the extreme statistical outlier is fundamentally flawed. This paradox forces physicists to seek models that naturally prevent such bizarre fluctuations. One solution is that the universe is not eternal into the future. If cosmic expansion driven by dark energy leads to a cold, empty, but ultimately finite future, then there is only a finite amount of time for these fluctuations to occur, shutting the door on the statistical absurdity. Another is that the vacuum of space is not eternally stable. If it can decay into a lower energy state, our universe has a finite lifespan, again cutting off the time needed for Boltzmann brains to dominate. The paradox acts like a cosmic litmus test, weeding out theories that lead to an absurd, solipsistic conclusion. It tells us that the hidden forces shaping the cosmos must conspire to create a reality that is not just possible but robustly, consistently real. The fact that we can have this conversation grounded in a shared and verifiable past is powerful evidence against an eternity of random chaos. We are not ghosts in a fleeting machine. We are witnesses to a universe that is genuinely, enduringly here, and its very existence hints at a deeper rule that keeps the madness of infinite probability at bay. If reality is not a random fluctuation, then perhaps it is part of a grander cycle of birth. The theoretical mirror of a black hole is a white hole. while a black hole's event horizon is a one-way street inward from which nothing can escape, a white hole's horizon is a one-way street outward. Nothing can ever enter a white hole. Matter and energy can only erupt from it, spewing forth into spacetime. It is a cosmic fountain of pure creation, and by its very definition, it exists only in the mathematics of general relativity as a time-reversed black hole. But what if these mathematical curiosities are not just abstractions? What if they are the engines of Genesis? One radical model suggests our own Big Bang was not a singular beginning from nothing, but the violent eruption of a white hole. In this view, our entire universe is the interior of a black hole that formed in a larger parent cosmos. The immense gravitational collapse that created that parent black hole did not end in a singularity from our perspective. Instead, it tunneled through to become a white hole explosion in a new region of space-time, birthing our cosmos. We are not the first universe, we are the offspring. The laws of physics we experience could be the unique imprint of that particular birthing event, the stretched and transformed remnants of the parent universe's physics. This idea inverts our cosmic perspective completely. The vast expanse we see when we look up is not an infinite void, but the interior of a celestial womb, its boundaries forever hidden beyond our cosmological horizon. The cosmic microwave background is not the afterglow of a beginning from nothing, but the cooled echo of that white hole's first brilliant flash. This leads to an even more profound cycle, a theory of cosmic reproduction. If a black hole in a parent universe can birth a new universe via a white hole, then every black hole in our own universe could be a portal to a new reality. When a massive star collapses, or when supermassive black holes merge in the hearts of galaxies, they may not be creating eternal prisons of darkness. They could be creating cosmic seeds inside every black hole beyond the event horizon where our physics breaks down. The compressed matter might not crush into oblivion. It could rebound, triggering a new inflationary Big Bang in a disconnected region of space-time, a baby universe with its own dimensions and physical constants budding off from our own. Our cosmos would then be both a parent and a child, part of an endless fractal tree of realities, each with its own unique physics, born from the death throes of stars in a universe above it. This hidden cycle offers a breathtaking symmetry. Death gives birth. The ultimate endpoint of gravity becomes a new beginning. A star's catastrophic end in our sky could be the first dawn of light in another. While we have no observational evidence for white holes, and they may be mathematically unstable in our universe, the concept forces a profound shift. It suggests that the hidden forces governing existence are not just about attraction and repulsion, but about transformation and legacy. The darkest objects we know might not be ends, but bridges, connecting our story to an infinite lineage of cosmic generations, each a secret held within the heart of a shadow. While string theory weaves reality from vibrating strings in extra dimensions, a radically different vision of quantum gravity has been taking shape. It asks a simpler, more direct question: what if space-time itself is not a smooth, continuous fabric, but is woven from individual threads? This is loop quantum gravity, a theory that does not seek to unify all forces, but focuses with laser precision on quantizing gravity itself. Its core philosophy is background independence, meaning it does not describe particles moving on a pre-existing stage of spacetime. Instead, the stage is built from the actors. The fundamental building blocks are not strings, but tiny, one-dimensional loops of gravitational field woven into a network. Picture the universe not as a sheet of rubber, but as an unimaginably dense, constantly evolving tapestry. Each thread in this tapestry is a loop of space, and where they intersect, they create a node. This structure is called a spin network, a mathematical object that represents the quantum state of space itself. The volume of space is not a smooth continuum. It comes from the number of nodes in a region. The area of a surface, like the event horizon of a black hole, comes from the number of loops that pierce through it. Space, in this theory, is fundamentally granular, composed of discrete, indivisible quanta at the Planck scale, a size a trillion times smaller than an atom. This granularity has a stunning consequence. It prevents the formation of true singularities. In Einstein's general relativity, the center of a black hole and the moment of the Big Bang are points of infinite density where the laws of physics break down. In loop quantum gravity, as matter collapses toward a black hole center, the density becomes so immense that it reaches the Planck scale. Here, the granular nature of spacetime resists further compression. The intense gravitational attraction is met with an equally powerful repulsive force generated by the quantum geometry itself. Instead of crushing into a dimensionless point, the collapsing matter rebounds. This leads to the theory's most beautiful prediction, the Big Bounce. Our universe may not have begun from a singular nothingness. It could be the rebound from a previous cosmic phase that contracted under its own gravity. In this cyclical model, a prior universe collapsed to an extremely dense state. Then quantum gravitational effects caused it to bounce outward, creating the expanding universe we see today. This offers a concrete, non-singular beginning, a cosmic heartbeat where each cycle potentially reshuffles the laws of physics. The hidden force here is not a particle or a field in space, but the very atomic structure of space and time. It suggests that if you could peer down to the absolute foundation of reality, you would not find smooth emptiness or vibrating strings. You would find a dynamic, shimmering web of relationships, a spin foam of evolving connections where geometry itself is born from quantum entanglement. While it lacks the unified ambition of string theory, loop quantum gravity provides a tangible, minimalist picture, a universe where the fabric of existence has a finite, elegant weave, forever preventing its own unraveling into infinite nothingness. The granular weave of space in loop quantum gravity suggests a dynamic beginning, but another theory questions a different constant, one we consider absolute. The speed of light in a vacuum is the universe's ultimate speed limit, a cornerstone of Einstein's relativity, enshrined as a fundamental constant, c. But what if this constancy is an illusion of our mature cosmos? What if light raced across the infant universe at a blistering, unimaginable pace? This is the variable speed of light theory, a radical alternative to cosmic inflation. It dares to ask if the horizon problem and the flatness problem, the very puzzles inflation was invented to solve, could be resolved not by hyper-fast expansion, but by a simple change in the rules of the game. The horizon problem asks why the universe is so uniform. Regions of space on opposite sides of the observable universe are so far apart that light, traveling at its constant speed, would not have had enough time since the Big Bang to travel between them and equalize their temperature. Yet the cosmic microwave background shows they are almost identical. Inflation solved this by saying these regions were once much closer together before a brief period of exponential stretching. The variable speed of light theory offers a different answer. If the speed of light was nearly infinite in the universe's first moments, then information and heat could have crisscrossed the entire cosmos in an instant, smoothing everything out before the speed dropped to its current value. It is like having a group of friends scattered across a vast field. If everyone can only walk, they will never meet to share news and become uniform. Inflation makes the field shrink suddenly so everyone is close, then expands it again. The variable speed of light theory lets everyone run at superhuman speed for a minute to exchange information, then forces them to walk for the rest of time. The flatness problem is similar. Our universe's geometry is incredibly flat, a precarious balance between expansion and gravitational pull. To have remained so flat for so long, the initial conditions at the Big Bang had to be fine-tuned to an absurd degree, like balancing a pencil on its tip for billions of years. A much higher speed of light in the early universe changes the equations governing this balance, naturally driving the cosmos toward flatness without any need for miraculous fine-tuning. Physicist Joe Megiddo has been a leading proponent of this idea, developing models where the speed of light varied in relation to other constants. In his theory, the change was not random, but tied to the evolution of the universe's density and temperature, a phase transition that locked light into its current, slower pace. The appeal is its stark simplicity. It replaces the complex mechanism of an inflattened field with a single, dramatic change to a constant we thought was immutable. But testing this idea is monumentally difficult. We cannot go back in time to measure the speed of light 13 billion years ago. Any evidence must be indirect, imprinted on the relics of the early universe. Some researchers have looked for subtle signatures in the cosmic microwave background, specific patterns in its polarization or temperature fluctuations that would differ from the predictions of inflation. Others suggest that a varying speed of light would affect how the first light elements formed during Big Bang nucleosynthesis, leaving a tiny fingerprint in the cosmic abundance of helium and deuterium. So far, no such evidence has been found, and the inflationary model remains the standard, supported by a wealth of observational data. Yet the variable speed of light theory persists as a powerful reminder. It challenges our deepest assumptions about what is truly fundamental. We hold constants sacred because they are the pillars of our equations, but the universe has no obligation to obey our sense of elegance. Perhaps the most hidden force of all is change itself, a law that even the speed of light must one day obey. Einstein's revolutionary leap began with a simple, almost poetic question. What if the resistance you feel when you push a shopping cart, that property of matter we call inertia, is not an intrinsic quality of the object itself? What if, instead, it is a gravitational conversation with the entire cosmos? This is the essence of Mach's principle, a philosophical idea that deeply inspired the young Einstein on his path to general relativity. The principle, named for physicist Ernst Mach, suggests that the distant stars are not just a backdrop. They are active participants in the physics happening right here in your living room. The inertia of an object, its resistance to being accelerated, would not exist if the rest of the universe were suddenly to vanish. It is as if every particle in your body is subtly anchored to the collective mass of all the galaxies, a hidden web of gravitational influence that defines what it means to be at rest or in motion. For Einstein, this was a guiding light, a hint that physics should be relational, that the properties of space itself are determined by the matter within it. Yet, when he completed his equations of general relativity, he found to his disappointment that they did not fully embody Mach's idea. The theory allowed for solutions like empty, rotating universes, which seemed to violate the principle that motion is only meaningful relative to other matter. The question was left hanging, a beautiful ghost in the machinery of his theory. Decades later, a stunning confirmation emerged from the subtle warping of spacetime itself. It is called the lens-Thirring effect or frame dragging. According to general relativity, a massive, rotating object does not just create a gravitational well like a weight on a rubber sheet. It also twists the fabric of spacetime around it, like a spoon spinning in a thick fluid. Any object moving near it will be dragged along with the rotation, its local frame of reference subtly twisted by the motion of the mass. This is not the direct gravitational pull of the mass, but a more profound influence on the very stage of space and time. In 2004, after decades of painstaking effort, scientists announced the results of the Gravity Probe B mission. They had placed 4 of the most perfect gyroscopes ever built in a polar orbit around Earth, their spin axes precisely aligned with a distant star. If frame dragging were real, Earth's rotation would very slowly tug on the fabric of spacetime around it, causing the gyroscope's axes to drift minutely over time. The experiment was a masterpiece of precision, needing to measure an angle shift equivalent to the width of a human hair seen from 250 miles away. The results were clear. The gyroscopes drifted exactly as Einstein's equations predicted. The Earth, by spinning, was literally dragging the frame of space and time around with it. This was a partial, breathtaking validation of Mach's intuition. Local physics here in orbit was being influenced by the distribution and motion of mass, specifically our rotating planet. But does this confirm the full, sweeping vision of Mach's principle? Not quite. The effect is incredibly small for an object like Earth. The true test would be the universe itself. If inertia truly comes from all the mass in the cosmos, then the distribution of galaxies on the largest scales should set a universal standard of non-rotation, a cosmic reference frame against which all local spinning is measured. Some theories, like Brand's-Dick gravity, explicitly build Mach's principle into their foundations, making the gravitational constant itself a dynamic field influenced by the matter in the universe. Others see it as an emergent property of a deeper quantum gravitational theory. The mystery endures because it strikes at the heart of what is real. Are the forces we feel and measure purely local phenomena, or are they whispers from the edge of the observable universe, a hidden consensus reached by every atom in existence? When you push against the inertia of an object, you might not just be fighting its mass. You could be pushing, in the faintest possible way, against the combined gravitational pull of 100 billion galaxies, a resistance written into the cosmos at its birth. The resistance of inertia connects us to the cosmos, but an even more intimate rule governs the very stuff we are made of. Deep within the atom, a silent law with the power of 1,000 suns holds the universe together, not by pushing or pulling, but by forbidding. This is the Pauli exclusion principle, a quantum commandment that states simply that no two identical fermions, particles like electrons or quarks, can occupy the same quantum state at the same time. It is not a force in the traditional sense. There is no particle exchanged, no field mediating the interaction. It is a fundamental rule of existence, a cosmic traffic law written into the fabric of reality that says, you cannot be here if I am already here. Without this rule, the universe would collapse into a formless, dense blur. Consider the humble atom. An electron whirling around a nucleus is not just a tiny planet in a solar system. It occupies a specific quantum address defined by its energy level, its spin, and its orbital path. The exclusion principle ensures that each electron in an atom must have a unique set of these quantum numbers. This forces electrons to stack into orderly shells around the nucleus, like guests filling seats in a theater from the front row back, rather than all crowding onto the stage. This shell structure is the sole reason for the periodic table of elements and the dazzling variety of chemistry. If electrons did not exclude each other, all of an atom's electrons would simply fall into the lowest, most comfortable energy state, clinging directly to the nucleus. Every atom in the universe would look essentially the same, and chemistry, life, and complexity would be impossible. The solidity of the floor beneath your feet is a direct gift from this principle. When you push your hand against a wall, the electrons in your skin are not physically touching the electrons in the wall. They are repelled by the exclusion principle. As the electron clouds from both surfaces are forced together, the principle mandates that the electrons cannot occupy the same space. This creates an immense effective pressure, a quantum mechanical resistance that we perceive as the solid, unyielding nature of matter. It is why you do not fall through the floor. The principle scales from the microscopic to the monstrous. When a massive star exhausts its nuclear fuel, it collapses under its own gravity. For stars above a certain mass, the collapse is so violent that it smashes electrons and protons together to form neutrons. The entire core of the star, a mass greater than our Sun, is compressed into a sphere the size of a city. What stops it from collapsing further into a black hole? The Pauli exclusion principle, now acting on neutrons. Just like electrons in an atom, the neutrons resist being squeezed into the same quantum state. This neutron degeneracy pressure creates a final, desperate stand against gravity, resulting in a neutron star, an object so dense that a teaspoon of its material would weigh 1 billion tons on Earth. The entire star is essentially a single, gigantic atomic nucleus held apart by this quantum rule of exclusion. It is a cosmic irony of breathtaking scale. The same principle that gives a feather its structure also holds back the gravitational abyss. The Pauli exclusion principle is the universe's architect of structure. From the diversity of elements to the hardness of diamond, from the glow of a neon sign to the deadly spin of a pulsar, it is the silent, non-negotiable rule that creates space, form, and difference in a world that would otherwise be a uniform, featureless sea of sameness. The Pauli exclusion principle builds the universe from emptiness, but emptiness itself is not what it seems. It holds a secret that depends entirely on who is looking, or more precisely, on how they are moving. Picture yourself floating in the deepest void of interstellar space. To you, the vacuum is cold, dark, and utterly empty. But now, imagine you fire your engines, accelerating through that same void at a constant rate. According to a startling prediction from the 1970s, your experience of that vacuum would transform completely. You would find yourself bathed in a faint, warm glow of particles. This is the Unruh effect, a quantum quirk that tells us reality is not absolute but deeply relational. The empty space of an inertial observer, someone floating freely, is not the same as the empty space of an accelerating observer. For the one accelerating, the quantum fields that fill the universe appear to be in a different state, a thermal state. The relentless acceleration excites the quantum vacuum, causing virtual particles to crystallize into real particles that the accelerating observer can, in principle, detect. The faster the acceleration, the hotter this ghostly bath of radiation becomes. It is a direct and profound cousin to Hawking radiation. A black hole's event horizon creates a barrier that, for a hovering observer just outside it, requires constant acceleration to avoid falling in. That acceleration, according to the equivalence principle, is indistinguishable from gravity, and it produces Hawking radiation. In both cases, an event horizon is key. For the accelerating observer in empty space, there is a Rindler horizon, a boundary behind them that information can never cross, creating the thermal glow. This bizarre effect is more than a mathematical curiosity. It suggests that acceleration has a fundamental interaction with the quantum vacuum, a kind of quantum friction. And this leads to a radical theory about the most familiar force of all, inertia. Why does an object resist being accelerated? The standard answer is mass, but that just names the property. Physicist Mike McCulloch has proposed that inertia itself might emerge from this very friction, the Unruh effect. His theory, called quantized inertia, starts with a simple but profound idea. When an object accelerates, information about that motion takes time to travel across the object. At the quantum level, this sets up a limit, a cosmic horizon. The Unruh radiation the object should see is not uniform because longer wavelength radiation cannot fit within this informational horizon. This creates an imbalance in the quantum vacuum pressure pushing on the object. More pressure pushes from the side opposite the acceleration than from the front, creating a net resistance to the change in motion. In this view, inertia is not an intrinsic property of matter. It is a force exerted by the universe's quantum vacuum, a hidden drag that appears whenever you try to change your state of motion. It is as if the vacuum itself has a kind of viscosity, and plowing through it requires effort. This idea makes a bold and testable prediction. In extremely low acceleration environments, like the faint gravitational tugs at the edges of galaxies, the Unruh wavelengths involved become so long they might be limited by the size of the observable universe itself. This alteration to the quantum friction could, McCulloch argues, explain galaxy rotation curves without any need for dark matter, and even account for the pioneer anomaly. The resistance you feel when you push a shopping cart in this theory is ultimately a conversation with the farthest reaches of the cosmos, mediated by the ghostly particles of an accelerating vacuum. While highly speculative and debated, the connection between the Unruh effect and inertia represents a breathtaking synthesis. It links the bizarre, observer-dependent reality of quantum fields to the most tangible experience of force in our daily lives. It suggests that the vacuum is not just a seething sea of potential, but an active participant in the laws of motion, a hidden medium whose subtle pushback writes the first law of Newton in quantum fire. The quantum vacuum's friction suggests reality responds to motion, but what if it also responds to thought? Our final theory ventures to the very edge of physics and philosophy, where the most hidden force might not be in the fields of space but within the mind itself. This is the consciousness causes collapse interpretation of quantum mechanics. It begins with the central, enduring mystery of the quantum world, the measurement problem. In the pristine mathematics of quantum theory, a particle like an electron does not have a definite position or spin until it is observed. Before measurement, it exists in a fuzzy superposition of all possible states described by a wave function. The act of measurement somehow forces this wave function to collapse into a single, definite outcome. But what exactly constitutes a measurement? Is it a physical interaction with a detector? The detector itself is made of particles also governed by quantum rules. This leads to an infinite regress, a chain of quantum interactions with no clear end. The consciousness causes collapse interpretation proposes a radical endpoint, the conscious observer. In this view, it is not the machine, but the awareness of the result in a mind that finally collapses the wave function, transforming possibility into actuality. The universe, at its most fundamental level, remains in a ghostly state of potential until a conscious being looks at it. This idea finds a famous and deeply unsettling thought experiment called Wigner's friend. Imagine a physicist, Eugene Wigner, outside a sealed laboratory. Inside, his friend conducts the classic double-slit experiment, firing a single particle toward a detector. According to standard quantum mechanics, until the friend looks at the detector, the particle exists in a superposition, having gone through both slits. But once the friend observes the result, the wave function collapses for him. He now knows definitively which path the particle took. Now Wigner is still outside. From his perspective, the entire laboratory, including his friend and the detector, is a quantum system. Until he opens the door and asks his friend for the result, Wigner must describe his friend as being in a superposition of having seen one result and having seen the other. Two conscious observers would then have contradictory accounts of reality. Has the wave function collapsed or not? The consciousness interpretation forces a stark choice. Either consciousness has a special, non-physical status that halts the quantum chain, or there is no single, objective reality until all conscious observers compare notes. This stands in direct opposition to the other great escape from the measurement problem, the many worlds interpretation. In that view proposed by Hugh Everett, the wave function never collapses. Instead, every possible outcome of a quantum event actually occurs, but in a newly branched parallel universe. At the moment Wigner's friend looks at the detector, the universe splits. In one branch, he sees the particle go through the left slit. In another, perfectly real branch, he sees it go through the right slit. Both Wigners, one in each branch, will later have a consistent story. There is no special role for consciousness, just an ever-branching multiverse where every possibility is realized. The contrast could not be more profound. One theory places mind at the center of reality, a cosmic sculptor that carves the definite from the possible. The other renders mind a passive passenger in an infinite fractal of realities. Its choice is merely selecting which branch it travels down. The implications of the consciousness interpretation are staggering. If true, it suggests that the bedrock of physical reality is not matter or energy, but observation itself. The universe may have remained in a latent, unrealized state for billions of years until the first conscious life evolved to perceive it. It introduces a kind of participatory universe where life is not an accidental byproduct of physics, but the very mechanism that brings physics into sharp focus. While most physicists dismiss this as mysticism, arguing that consciousness must emerge from complex physical processes and not the other way around, the puzzle remains unresolved. The measurement problem is the open wound of quantum mechanics, and until it is healed by a testable theory of quantum gravity or something even deeper, the possibility remains, a haunting whisper that the final hidden force shaping existence might be the act of paying attention. That final, haunting whisper brings us to the end of our journey through 30 glimpses into the universe's hidden rulebook. We began with the ghostly push of dark energy, a force woven into empty space itself, and ventured through the shadowy realms of dark matter and the radical possibility that gravity itself might be an illusion. We explored cosmic holograms, multiverses bubbling in an eternal sea of inflation, and the seething quantum foam that underlies our quietest vacuums. We confronted black holes that might be cosmic batteries, a fifth force carried by dark photons, and the chameleon field that hides in plain sight. From the unsettling axis of evil etched in the first light to the great attractor pulling us through the dark, from the paradox of information in black holes to the statistical nightmare of Boltzmann brains, each theory is a testament to human curiosity. We wrestled with the simulation hypothesis, cycled through universes born from colliding brains, and chased the dream of a single theory of everything in the vibrating strings of extra dimensions or the woven loops of quantum space. We saw how fine-tuning leads to the anthropic principle, how quantum entanglement weaves the fabric of reality, and how even the humble Casimir effect proves nothing is truly empty. The hunt for magnetic monopoles, the lessons of the pioneer anomaly, the arrow of time, the silence of the Fermi paradox, the cosmic bounce, a speed of light that could change, the frame dragging of our planet, the exclusion principle that builds solidity, the Unruh effect's thermal glow, and the ultimate question of consciousness itself. Each is a different path up the same mountain, a search for the hidden architects of reality. This relentless questioning, this drive to peek behind the cosmic curtain, is not just a collection of ideas, it is the very engine of discovery. Every paradox, every anomaly, every quiet whisper from the data is a clue waiting to be decoded, pushing the boundaries of what we know and redefining what is possible. Our understanding of the cosmos is not a finished book, but a living story, rewritten with every new observation and every bold thought. So, what did you find most compelling on this journey? Was it the holographic universe, the chilling possibility of a great filter, or the elegant terror of the Boltzmann brain? Share your favorite theory in the comments below. Let us know which hidden force captured your imagination. And as we stand on the edge of this vast unknown, looking out at a cosmos filled with more questions than answers, what do you think the next great revelation will be? The discovery of a dark photon, proof of a multiverse, a final theory of quantum gravity. The search continues, and the next chapter is being written right now, in labs and observatories and in the minds of curious people everywhere. If you want to join that search, to dive deeper into the mysteries of space, time, and existence, be sure to subscribe. Our exploration of the cosmos has only just begun.